Hey everyone! So today we are building on our thermochemistry knowledge a little bit, and we're going to talk about calorimetry. So calorimetry is pretty much the study of heat transfer. So what chemists do nowadays is that they make chemical reactions happen in this nice little container called a calorimeter, and after that reaction happens, they measure how much heat is released. So we'll be doing a little bit of that today, but we're going to focus mainly on the specific heat of certain materials. So let's talk about specific heat. Specific heat, it's a value given that just tells you how easy a certain material is to heat up or cool down. So specific heat is just a number that tells you how easy it is to heat it up, a material. Okay, so again, it's just a number, and water has a specific heat, aluminum has a specific heat, lead has a specific heat, and all that number does is it tells us how easy it is to get something hot. Okay, if you think about real world metals that you're dealing with, something like when you put a pot on the stove burner for a little bit, it doesn't take very long for the pot to get hot, but it does take a while for the water to get hot. So maybe after a minute you could touch the pot and it's able to burn you, but after heating the water for a minute, if you put your hand in the water, it isn't hot. So that's specific heat. Water has a really high specific heat. So let's talk about that a little bit. Let's say that I got just a 1 gram block of aluminum. And let's say that I have a 1 gram block of lead. So I got the same amount of aluminum and I've got the same amount of lead. And let's just say that I'm trying to increase the temperature from 1 degree Celsius to 2 degrees Celsius for both of these guys. Okay, so same amount of each of these metals, and I'm just trying to heat them up by 1 degree. Well, with aluminum, it might take something like, let's say, 10 joules of energy. That's not true, but let's just say it takes 10 joules of energy to heat this up. Well, lead is a lot easier to heat up than aluminum, so lead might only take 1 joule of energy to heat up 1 degree. And that has to deal with ionic charges of these metals, which we will talk about at a later date. So that's what we're going to deal with. We're going to talk about specific heat, and we're going to be dealing with calculations involving specific heat. So aluminum's specific heat in real life is actually 0.9 joules per grams degrees Celsius. And lead's specific heat is typically 0.13 joules per grams degrees Celsius. So it only takes 0.9 joules to heat 1 gram of aluminum 1 degree Celsius. Okay, so my 10 joules should actually be 0.9 joules. And for lead, it only takes 0.13 joules of energy to heat this 1 gram of lead by 1 degree Celsius. So this should actually be 0.13 joules, okay? So those are the specific heat. The higher it is, the harder it is to heat. Something like water, it has a specific heat of 4.186 joules per grams degrees Celsius. So it takes 4 joules of energy to heat 1 block of water 1 degree Celsius, okay? So that is specific heat. So now let's go ahead and let's talk about the calculations that we're going to be doing involving specific heat. So now we're doing our calculations involving specific heat, and it deals with one equation, which is fun to say. It's kind of like PIVNERT, but it is QSMAT. Okay, QSMAT is our calculation that we're going to be doing. What does Q stand for? Q stands for energy, okay, which is measured in joules. S is that specific heat we were talking about, and it's different for each material we're dealing with. And its units are joules per grams degrees Celsius. M is mass. And now we're back to our units of grams. I know with energy we've been talking about kilograms when it deals with potential energy and kinetic energy. But now that we're back to QSMAT, we're dealing with grams. And then remember that delta stands for change in. So we're dealing with delta T, which is change in temperature. And this is typically in Celsius. Okay, if it's in Kelvin, you could leave it in Kelvin because the change in temperature is the same. If you change 10 degrees Kelvin, it's the same as changing 10 degrees Celsius. It's just going to be off by a factor of 273 degrees. So that is the equation that we are using. We got Q, S, M, and delta T. So let's do a couple examples with QSMAT now. So here's our first example. How much energy does it take to heat 25 grams of copper from 25 degrees Celsius to 75 degrees Celsius? And then right here, I have a S with a sub Cu. So that's the specific heat of copper equals 0.395 joules per grams degrees Celsius. So I look at this equation, I see a specific heat right off the bat, and the only equation that we deal with that has specific heat is QSMAT. Okay, QSMAT. So we're looking for energy. I also might say heat. They are the same in this instance. Okay, so we're looking for Q. Specific heat I gave you, right? It was 0.395. Mass is measured in grams, right? And I gave you 25 grams. It's in the right unit, so we'll just put 25 in there for M. And then remember, change in temperature is always final minus initial. Change in anything is always final minus initial. So in this case, our final temperature, we're heating it from 25 degrees to 75 degrees. And we're going to subtract our initial temperature, which was 25 degrees Celsius, which is going to be 50 overall. Okay, so I'll go ahead and take 75 minus 25, and that will equal 50. That is good to know because sometimes I might give you energy, I might give you specific heat, I might give you mass, and I might give you temperature final, and I might want to know temperature initial. Okay, we'll deal with that later. So let's go ahead and let's solve for this. So we got our specific heat, we got our mass, and we got our change in temperature, which was 50 degrees. So I'm going to get out my handy dandy calculator here. I'm going to take 0.395 times 25 times 50, and I'll get 493.75. Let me double check. Yep. And that's going to be joules. Right? So that is our first example. Let's go ahead and let's do another example. So our next example says a 90-gram sample of an unknown metal absorbs 25.6 joules of heat, and its temperature raises 1.18 degrees Celsius. What is the specific heat of the metal? So once again, it's asking for specific heat. Well, the only equation we have that even involves specific heat is QSMAT. So let's go ahead and let's plug in what we know. We're looking for specific heat, right? So we should be able to plug in Q, M, and delta T. Q is energy, right? This says absorbs 25.6 joules of heat, so that is our energy. Specific heat is what we're looking for. Our mass, it's a 90-gram sample, so that's nice. They put it in grams for us. And our change in temp, it says the temperature raises 1.18 degrees Celsius, so that is our change. Right? They didn't have to give us a final or an initial. They just gave us the change altogether. It rose 1.18 degrees Celsius. So now all we got to do is get specific heat by itself. Well, that's pretty easy. We just divide by 90 and 1.18 on both sides. That way, specific heat gets by itself. So let's go ahead and let's take 25.6 divided by, in parentheses, 90 times 1.18. And we get a specific heat of 0.241, which it takes 0.241 joules to raise 1 gram of the metal 1 degree Celsius. All right. Remember, I said that aluminum had a specific heat of 0.9 joules per grams degrees Celsius. So which one's easier to heat up? our aluminum or our unknown metal? Our unknown metal is easier to heat up. It's got a smaller specific heat. It only takes 0.241 joules to raise it 1 degree, 1 gram of it. Aluminum takes 0.9 joules to raise it 1 degree Celsius if you have 1 gram of it. You commonly notice this with aluminum when you are cooking with it, right? If you use aluminum foil in the oven, the pan, which is made out of like some type of iron, okay, it heats up a lot easier. You hold on to it, it could burn you. But aluminum foil, you could grab that right out of the oven and it won't be hot at all. It won't burn you. And that's just because aluminum has such a high specific heat that takes a lot of energy to make it hot. Let's go ahead and let's do one more example. So here is our final example. 10 grams of water initially has a temperature of 25 degrees Celsius. If the water absorbs 500 joules of energy, what is the final temperature? So we're dealing with mass, we're dealing with the energy, we're dealing with some temperatures. The only thing they didn't give us is specific heat, and that's the one thing that you have to know. You have to know the specific heat of water. It's the only one that in the science world they kind of expect you to know all on your own. And the specific heat of water is just 4.186 joules per gram degrees Celsius. So if they didn't give you specific heat, you could see that you got mass, you got temperature, you got energy, and you want to know the final temperature. That sounds like a QSMAT problem to me. It deals with energy, mass, temperature. That's the only one that we have that really deals with energy, mass, and temperature, right? Kinetic energy doesn't deal with temperature, even though it does deal with energy and mass. So what we'll do is, we know we're dealing with water. We'll know it in our heads that the specific heat is 4.186. And then we'll say, okay, let's start plugging and chugging and see if we can figure out this final temperature. So again, we're going to use QSMAT. We know that Q is 500 joules because that's the amount of energy it absorbs. Specific heat is 4.186. Mass is 10 grams. And delta T, you might be saying, okay, I just plug in 25 degrees Celsius. Remember, delta T is temperature final minus temperature initial. So sometimes I give you the initial and final temperature. Sometimes I just give you the temperature change. Here, the only thing I gave you was the initial temperature, right? The water is initially at a temperature of 25 degrees Celsius. So now we have to figure out the final temperature, right? What is the final temperature? So we've plugged in everything we know. The only thing we can do from here now is try to solve this algebraically. TF minus 25 has to be treated as a variable all on its own, okay? So we can't mess with that until it's by itself. So let's go ahead and get TF minus 25 by itself. Let's divide by 4.186 times 10 on both sides. So I'll take 500 divided by 4.186 times 10. And I get something like 11.94 equals TF minus 25. Okay, we got rid of 4.186 and 10. We simplified this. Now I got to get TF by itself. So to do that, I just got to add by 25 on both sides, right? That gets rid of 25 on the right. If I add 25 on the left, that should give me my final temperature. So 11.94 plus 25 gives me a temperature final of 36.94 degrees Celsius. I might ask you, is that enough to boil the water? No. It's got to be at 100 degrees Celsius to boil water, right? So not quite enough. And you could actually calculate how much it would take for you to how much energy you'd have to add to water in order for it to boil at 100 degrees Celsius. So that's it. That's calorimetry. That is QSMAT in a nutshell. Make sure you understand how specific heat tells you how easy it is to heat up a metal. Make sure you know how to use the QSMAT equation to find energy, maybe mass, maybe temperature change, maybe temperature initial, temperature final, and how to find specific heat with QSMAT. That's today's lesson. Let me know if you have any questions. Have yourselves a great day.